Good afternoon, everyone, and welcome to day one of reInvent. We're very pleased to have you all join us to discuss training high-performance AI models on AWS using SageMaker. I am Michael Ogwike. I'm a senior product manager on Amazon, and I work on AWS SageMaker, where we help customers train high-performance models. With me today is Tomomori Shimomura, who's a principal solutions architect who also works on SageMaker and helps customers train AI models. We're very pleased to be joined by Denny Gupil, who's also a principal machine learning scientist from Roblox, and they're going to be sharing an exciting use case with us. Today, we're going to go through the need to train large AI models. We're going to discuss the challenges that we see in training these large models, and then we'll discuss how SageMaker helps to resolve these challenges. Then Tomomori would come back up and show us an actual demo, followed by Roblox, with Denny coming back up to show us a real-life example of how they've built a 4D foundational model using SageMaker and Hyperpod. Before we go on, by a quick show of hands, how many of us in the audience have trained or customized a large model? Okay. And how many of you have done that using SageMaker? Great. So there's going to be a lot of capabilities that we'll share and a lot to also learn here. But before we even go deeper, I think a couple of you may have noticed the growing popularity of this sparkle icon. You may have seen it on your reInvent app, where it's helping you to try to get more out of your week. Or you may have noticed it on your playlist, where AI is trying to help you create a better playlist. Or even on autonomous driverless cars on the road. For me, even while building this presentation, as I was trying to crop photos, AI was there trying to help me crop my photos better. But behind each of these icons is a trained model. And as your customers and your users are getting more used to using AI to improve their experience, you're also going to be needing to add more capable models to the experiences that you already deliver for your customers. And in fact, we see this in studies. A study by McKinsey showed that 47% of companies who said they were using generative AI were also training or customizing these AI models to better serve their use cases. Now, we built SageMaker for AI. As we've seen the trend moving on forward for you to help to build more capable models for your customers, it's important that we have the right capabilities for you, our customers, to build and train and deploy these models. We started this journey in 2017 when we launched SageMaker Training Jobs. SageMaker Training Jobs offers you a fully managed API where all you need to do is bring in your training data, you bring in your training script, you tell us which instances you want to run, and we take all that input, we spin up a cluster, we train the model, and we deliver the model artifact to an S3 bucket. It's an ephemeral cluster, and you only pay for what you use. And our customers had a great experience with that, and they continue to use Training Jobs. But then we had customers like you ask for more capabilities, such as being able to manage the cluster using Slurm or Kubernetes. We had customers asking for more granular control and observability to these clusters. And there were also customers who wanted more persistent clusters, so they could both run training jobs and inference jobs on the same infrastructure. So we launched SageMaker Hyperpod to meet these needs. So in the conversation today, and the two key capabilities that we have are, one, SageMaker Training Jobs, which is the ephemeral compute, or SageMaker Hyperpod, which is more persistent. These are the two key services that SageMaker offers for you to train your models. As we've continued to work with you and other customers to learn about what matters most to you for training large AI models, we've seen 6 key dimensions. 1, compute availability. 2, performance. Then there's resiliency. There's observability. Number 5, ease of use. And most importantly, cost. Every lever that we move on each of these 5 dimensions has a direct impact on your cost. And in the next couple of slides, I'm going to dive deeper into the first 3, compute availability, performance, and resiliency. And when Tomonori comes up, he's going to go deeper into observability and ease of use when we walk through the demo together. With compute availability, let's first of all look at the trend that we've been observing over the last couple of years. We've seen that over the last couple of years, we've been needing to use more compute to train more capable models. This is primarily driven by the fact that we need more training data, and we're also training these models with more parameters so they can be more capable, they're more accurate, like using them in cases like in the legal field or in the medical sciences or in autonomous driving. We need bigger models so they are more capable. Now, over the last 2 to 3 years, we've actually gotten to the point where we're now using 10 to the power of 24 flops of compute power to train these very highly performant models. And the scientific notation for 10 to the power of 24 is, wait for it, it's a yottaflop. But let's make that more concrete. What's a yottaflop? 5 yottaflops is the equivalent of running 1,000 P5 GPUs consistently for 1 month. That's a lot of compute power. That's very expensive. And that's why it's essential that we optimize the utilization of these GPUs. But we also want access to the most performant compute so we can get our training jobs done quickly. To do this, SageMaker offers multiple capabilities for you to get the best compute whenever you want it. So we have a wide selection of GPUs and accelerators, from the H100 single GPUs to GB200 Ultra servers. You can get single GPU jobs or even a 72 GPU Ultra server within a rack, depending on your needs. But that's one thing, selecting the GPU. We also understand that your business needs and your timelines are different. So we have various options to secure capacity, whether that's using on-demand capacity, or you can get spot capacity for up to 90% cheaper than on-demand capacity. And in fact, just last week on SageMaker HyperPod, we launched support for spot instances, which is great for fault-tolerant workloads and experimentation. Or if you want a longer-term reservation where you have guaranteed capacity, you can get a 1-year reservation or 3-year reservation with reserved capacity. And if you're looking for something in between, where there's a calendar period, say next month, you want to get capacity for a particular period of time, you can use the flexible training plans. Well, now that we've got GPUs, what are we going to do with them? As important as it is to get the compute capacity, it is even more important that we utilize them effectively to avoid wastage. With SageMaker, you have the option to use the training jobs managed API, where you just submit the job and we handle the scheduling and the distribution of the jobs across the GPUs. Or you can also use Slurm and Kubernetes, depending on what your scientists are more familiar with. Or if you have a team where you have multiple team members and you have different type of jobs, and you want to prioritize the different jobs, you want to allocate capacity to different teams within your organization, you can use a capability we call task governance on HyperPod, where you can allocate resources to different teams, or you can give a higher preference to, say, an inference job over a training job. And whenever an inference job comes, it preempts the training job. We also have an integration with AWS Batch that also allows you to do this with SageMaker training jobs. All these capabilities come together to ensure that you have the right compute capability and you're able to optimize utilization of these GPUs or accelerators, so you reduce your cost for training. We then talk about performance. And to discuss performance, let's quickly demonstrate the relationship between the amount of memory required by the parameters in a model compared to the available memory per GPU for a lot of the latest GPUs and accelerators. On this chart, we have two trends. There's one trend that's showing the higher incline, which shows the number of parameters in a lot of the popular models over the last 10 years. And we can see, like we talked about earlier, this growth in the number of parameters required for these large models. On the other hand, on the gentler slope, we can see the slope on how the memory per GPU is changing over time. And we can see that the number of parameters is growing faster than the memory per GPU. Now, the implication of this really, we can demonstrate this with one example, say the Llama 3 70B model. The amount of GPU memory that we need to train a 70 billion parameter model, we can calculate that by getting the amount of memory each parameter requires. And on average, the rule of thumb is like 18 to 20 bytes when you account for the weights and you account for the gradients and the optimizer states. So we say 20 bytes times 70 billion parameters, that requires almost 1.4 terabytes of data, of memory on the GPU. Now, even the NVIDIA H100 is 80 gigabytes of memory. So you do not have enough memory per GPU to load and train the model. So to overcome this scaling challenge, we then have to do what we call distributed training. And some of you are probably familiar with this, so I'll go over this quickly. But basically, for example, in the Llama 70B model case, where we have more parameters and more memory from the model than we can put on one GPU. What we then do is to shard the model across the different GPUs and distribute the training across the different GPUs. And as training happens in step, synchronously, the different GPUs can then communicate across each other to update their state. But then the data is small enough for us to replicate the data across the different GPUs. So each GPU is actually doing a micro batch of the training and then updating state as they go along. And that's model parallelism, where we split the model, but we replicate the data. Conversely, if we have a large training data set, but we have a small enough model, say a Llama 3.2 1 billion parameter model that we can fit onto one H100, because again, it's 20 gigabytes of model versus 80 gigabytes of GPU memory. In that case, we can split the training data across the different GPUs, replicate the model across the different GPUs, do the training in batches, and have all the GPUs synchronize state as they train over steps and epochs. One thing we might observe here is, at this point, the networking becomes very important because the GPUs have to update state and communicate with one another over time. If we even step one step more complex, where we are both distributing the training data as well as sharding the model, we've sharded the model across various layers in the neural network. We've also sharded the model across different tensors. So in this case, we're doing a hybrid of both data parallelism and model parallelism. But what's most important here is that your networking can quickly become a bottleneck. You need high bandwidth, low latency communication between all the nodes to ensure that you're not spending more time than you need on the training job. SageMaker offers multiple capabilities to ensure that you're getting the most performant, high-speed networking when you're running these training jobs. First, we have an automated, easy setup where you can use the CLI, SDK, CloudFormation, or even the console to set up your distributed training job. We have access to multiple popular frameworks like PyTorch, TensorFlow, or even Ray. And on the communication libraries, you can use NVIDIA Nickel, or if you're using Trainium instances, you can use the Neuron collective communication libraries. And for high-speed networking, you have access to the NVLink technology from NVIDIA, or for internode connectivity, you have access to elastic fiber adapter from Amazon, where you can get up to 3,200 Gbps of bandwidth. All these together help to ensure that you have an efficient distributed training setup where your GPUs and your training jobs are connecting and moving at a very high speed, which is essential for reducing your time to market and being cost efficient. Finally, we talk about resiliency. To discuss resiliency, we'll quickly bring back our favorite single GPU. Each of these GPUs has a mean time to failure. And when we scale these GPUs to a large number, say hundreds or thousands of GPUs, we then move from a GPU level resiliency to a job level resiliency, because every failure from every GPU in the cluster can potentially interrupt the progress of your entire job. And we've actually seen this in research. So research from Meta that was published in IEEE early this year showed where they ran an experiment on 2 large state-of-the-art clusters for about 11 months. And if you follow the lower line, they saw that for jobs running with 1,024 nodes, the average time to failure was about 8 hours. So that's 3 failures in one day. 1 for breakfast, 1 for lunch, and 1 to wake you up at 2 o'clock in the morning with a page. But how does SageMaker help us resolve these issues and prevent us from getting paged? We have a 4-pronged strategy: mitigation, prevention, detection, and recovery. And the way we achieve this is basically with mitigation. We encourage and we make it easy for you to checkpoint your training. So you're taking multiple saved steps. So even if something goes wrong 2 days, 1 week into the future, you're not losing all your training progress, and we're able to restart from a checkpoint. Sometime this year, we also launched managed tiered checkpointing, which basically reduces the penalty of having to checkpoint frequently, because there could be network penalties or even storage penalties. But with managed tiered checkpointing, you have a more efficient, faster checkpoint process, and you see that when Tomonori also shows his demo. For prevention, we have multiple types of health checks, with standard health checks or deep health checks, where essentially before we add a node to your job, we do a burn-in test and we really pressure test these instances. So if there's actually a problem with any of these instances or GPUs, we can isolate that instance from the cluster so it never even makes it into your cluster. For detection, we have automatic health monitoring agents that are continually running through the cluster and running through your job to identify any issues and resolve them. And then finally, for recovery, in the event that something does happen, we identify like there's a slow GPU or a slow node, we can automatically reboot the node, or if that doesn't resolve the issue, we will automatically replace the node and then restart the job from your checkpoint. So once again, all these capabilities come together, and we've seen cases where it saves up to 40% of the time spent on training, which essentially helps you save on your overall cost because you're able to respond to failures faster. So I'll now invite our Tomonori on to show us a demo of these in action. Thank you.
Yeah, thank you, Michael. Am I audible? Yeah, thank you. So I'm Tomonori Shimomura, Solutions Architect on SageMaker AI organization, helping SageMaker AI customers every day. And now Michael covered the fundamental concept of SageMaker AI's training capability. So let's dive deep into the actual developer experience, including demonstration. So as Michael explained, there are 2 training capabilities, SageMaker training jobs and Hyperpod. SageMaker training job provide free managed APIs. So before executing the job, SageMaker training job automatically create a cluster, and after the execution of the job, it automatically deletes the cluster. So essentially, the computer resource is allocated only during the job execution. So you can expect a lower cost. And you can use high-level Python SDK, and it's a kind of wrapper Python library on top of SageMaker's service API. And you can easily use SageMaker's training capability by writing Python code or running notebooks. And because this is based on the SageMaker service API, you can easily integrate the training job with your MLOps pipeline. This is an example code fragment of training job. And as you can see, this Python code is importing a Python module called SageMaker Core and instantiating, creating a training job object by passing some parameters like a hyperparameter configuration, instance type, instance count, and a container image. Right? By providing these parameters, you can configure the training job, start the training job, and automatically create a cluster internally. And another training capability from SageMaker is Hyperpod. And unlike SageMaker training job, Hyperpod is for persistent clusters. So it means cluster creation is not automatic, unlike SageMaker training job. And that you need to explicitly create and delete the clusters. But the Hyperpod helps you create such a high performance cluster easily. So you can customize the cluster based on your needs and share the cluster with your teammate, multiple users, and execute multiple jobs on the same cluster. That's the difference from the SageMaker training job. And as Michael said, SageMaker comes with advanced resiliency capability. I'd like to explain a little bit more later, and I also included some demonstration in my video. Yeah. And because SageMaker Hyperpod is for AI development purpose, right? Not a normal cluster. So it's an AI development purpose cluster. So it comes with AI purposed comprehensive observability dashboard, and also some useful libraries and tools to optimize your training. Hyperpod supports two orchestrator options. One is Slurm, and another is EKS or Kubernetes. EKS is Amazon's Elastic Kubernetes service, and it's actually Kubernetes. Okay? And both supports, I think Slurm and EKS are both powerful framework to run distributed training, but the developer experience are different. So I'd like to explain how they are different briefly. So Slurm is an open source job orchestration framework. And you can basically run a same batch job on multiple nodes. Simple word, right? And in case of Hyperpod, you will create three types of node: controller node, computer nodes, and login node. Typically, you log into login nodes and execute Slurm commands such as srun, sinfo, sbatch, and sq, etc. to run Slurm features. And another orchestrator is EKS or Kubernetes. I think many people have heard of Kubernetes because it's popular, right? And Kubernetes is a framework to run containerized applications, various types of containerized applications, including distributed training applications. And unlike Slurm orchestration, in case of choosing Kubernetes, the Hyperpod cluster only contains computer nodes because control plane, EKS plays the role of control plane. Hyperpod cluster itself doesn't contain control plane or login nodes. And you can run, Kubernetes clients like a kube controller or your preferred Kubernetes client on your development machine, even on your local laptop. Right? Yeah. So which is better choice for you? This is a tough question because this is case by case. So if you already have a preferred choice of orchestration, please choose it. And if you have want to directly access hardware, if you want to run application on host level directly, Slurm may be right choice. If you love containers, maybe Kubernetes or EKS may be the better choice. Yeah, I think Michael already covered some portion of resiliency, but let me recap quickly before going to the actual demonstration. So Hyperport resiliency, resiliency consists of 3 steps, right? Health monitoring, instance replacement, and the job auto-resuming. So these 3 are the core flow of Hyperport resiliency. So Hyperport constantly run health checks, and if it finds some faulty GPU faulty instance, we trigger the instance replacement. And after the instance replacement, the suspended job automatically resumes. We provide such a framework. Yeah, so we would like to do 2 demos. I captured pre-recorded videos, and partially I accelerated the video because in order to fit this in limited time session. So starting from SageMaker training jobs, and I'm going to open a code editor on browser. SageMaker has a code editor browser, by the way. And I execute a notebook in order to trigger the training job. And eventually, we will see the execution result training metrics by MLflow. Yeah, so firstly, I'm opening code editor on SageMaker, clicking open button. And it looks like a Visual Studio, right? So this is based on the open source version of Visual Studio code editor. And browsing the training code. This is the code actually executed on compute resource. And I'm executing notebook. And the first half of this notebook is for data pre-processing and uploading to S3 bucket. This is a preparation step. Yeah, visualizing the training data set and configuring some parameters for training job, like uploading S3. Right. And then configuring the training job. Yeah. Yeah, so you can see a model trainer class. I'm instantiating model trainer class with some parameters. This is the Python API. And then actually, configuring input channels, the input data channels, and starting the training. And you can also see the list of SageMaker training jobs on SageMaker management console like this. So now it's showing training status. Training is in progress. And the progress can be also seen by visiting CloudWatch logs management console. You can see output from container, right? Yeah. So there are some options how to monitor the progress. You can see CloudWatch logs. You can use also a notebook by calling some method of Python object. You can get the log output as well. And also after this, I will show, but you can also check MLflow output or your preferred observability solution as well. So SageMaker has MLflow, managed MLflow. So I click the MLflow button and opening the MLflow. And I'm seeing a list of executed training jobs. And you can see training metrics like this. Yep. So next demo is SageMaker Hyperport. And in this demo, I'm going to create a cluster easily and configuring, so customizing the cluster by installing some add-ons and running some training job. And I'm going to, so in this demo, I did simulating some hardware failure artificially by injecting a simulated error and verify that hyperpod resiliency works, and eventually see the observability dashboard. Yeah, so you can easily create a SageMaker hyperpod cluster. And in case of quick setup, what you have to do is just to choose right instance type and instance count. Basically, that's it. So cluster creation can be complex if you do manually, but we provide such a easy setup experience. And the actual cluster creation progress can be monitored on CloudFormation management console, because it requires not only cluster itself, but also require various prerequisite resources such as VPC or subnet, security group, S3 bucket, and IAM role, etc. Right? And when a hyperpod cluster is getting created, we can visit the SageMaker management console and see the instance initialization progress at the instance level. Now, so yeah, I think you just saw a deep health check was being executed. Now let's install some add-ons. Starting with hyperpod observability add-on, it's just literally one click. But although I'm enabling some additional, say, advanced metrics, so it's not a one click, but literally say one click in case of basic installation. And then enabling hyperpod task governance. This is for task prioritization and a dynamic compute quota allocation between multiple teams. This is useful in case of sharing a cluster between multiple teams and multiple purposes. So I'm configuring the priorities, job priorities depending on the task types, like inferencing, training, or experiments. And I'm also configuring two teams, Team A and Team B, and defining 8 instances as a default quota, but allowing lending and borrowing compute resource between teams. And then I'm configuring training job. Right? So as you can see in the second line, hyperpod training job, it's a custom resource definition installed by a hyperpod training operator, and I'm using it for advanced training. Installing additional software and modifying the checkpointing code in order to enable managed tiered checkpointing. I will explain more later. Yeah, so using some SageMaker specific Python classes for checkpointing code. Now on terminal, I'm monitoring 3 information. Top left, I'm monitoring the node status. Top right, pod status. And center is log output from training job. I executed the training job using kube control, very standard CLI interface. Right. Yeah, training is progressing. Next, I'm going to inject artificial GPU failure in order to simulate and verify the resiliency capability. So a good feature of hyperpod is you have direct access to the infrastructure. So not at the container level, not only just monitoring logs, but you can log into compute nodes like this by SSM session. And in this case, I injected some error message to the kernel log to simulate hardware error. And you can see, so one node became not ready status. And one pod, I think it became pending status. So it means your job got suspended because of the artificially injected error. And so new node came in thanks to the instance replacement. And a new container is creating status now. And soon it should start executing. So container, say newly created container started and job resumed like this. And then, job resumed. The next step, I'd like to show you how the observability dashboard look like. This is based on Prometheus and Amazon managed Prometheus and Amazon managed Grafana. So I'm using task, say, cluster dashboard first. The cluster dashboard shows you hardware resource related information at the cluster level or instance level, like this. And next dashboard I'm showing is task dashboard. It's pretty powerful. You can see key metrics like CPU, GPU, say memory utilization at the task level, not the instance level. So because Hyperpod is for distributed, so useful for distributed training, right? So I think you are interested in which team is using GPU efficiently, which team need improvement, and which job is, let's say not performing well because of what bottleneck, right? So those informations are really important to use cluster. So this observability dashboard is very useful for you. Okay, so in the demo, I included some newly introduced features this year. So let me highlight some new features. The first feature I'd like to highlight is enhanced Hyperpod, say, cluster creation experience on management console. And you can easily set up cluster by, entering some parameters. And configuring cluster can be very complex because, you need to not only configure the cluster itself, but also prerequisite resources. But you can use this browser-based experience to easily configure a cluster. Next feature is one-click observability. And observability is important for you, as I said, but setting up is complex because it requires metric emitting component on the cluster itself, and data time series database, and a visualization layer. But you can literally install this by one click. And the Hyperpod training operator, this is for efficient distributed training, and it has capability to recover intelligently. It has a job hanging detection. Managed tiered checkpointing. This is to reduce the overhead of checkpointing. And this is a feature I didn't include in my demo, but AWS, training job has a new feature, AWS batch support, and training job itself doesn't have a batch scheduling, job scheduling capability. It just run training. But by combining SageMaker training job and AWS batch, you can enqueue training job in a queue and intelligently scheduled by priority. And this is also a new feature I didn't include in a demo, but now you can run IDEs and notebook on Hyperpod cluster. So you can use Hyperpod cluster not only for running training jobs, but also for interactive development and experiment. And lastly, we released MCP server for SageMaker AI. So you can use this MCP server to create and maintain Hyperpod cluster by natural language. For example, you can say create a cluster with 4 G5 12x instances, or you can also say scale up my cluster from 4 instances to 8 instances by natural language. Okay. So now we covered fundamental concept of SageMaker training capability, and I provided some demonstration. Now I think you are interested in what Hyperpod or SageMaker AI capability can do in real world, right? So I'm interested, thrilled to introduce Danny Gopio from Roblox. his team is using SageMaker Hyperpod for one of core component of their AI platform. Cool.
Thank you. Hello, can you hear me? Cool. Yes, so I'm Denis. I work at Roblox, where I lead the AI infrastructure and AI platform team. And so today I'm going to talk about AI at Roblox to give you some context. And then we dig into our training infrastructure, especially how it has been impacted by training our 4D foundation model. And I finish by what we want to build next. So if you're not familiar with Roblox, Roblox is a platform where millions of people come together to create, play, and interact with each other with one of the million experiences that we have. And those experiences has been created by our community of creators. And so as of last quarter, we have 150 million daily active users, and we hit a 45 million peak concurrency. That means that 45 million people come together to play at the same time in Roblox. That's pretty huge. And in terms of AI, our AI infrastructure supports about 1 million plus query per second across our 350 plus 50 model that we have running in production. So as you can see, AI is pretty much everywhere on what we do at Roblox. And especially when it comes to safety, which is core to our principle. We train and we serve a model for real-time moderation, for voice and for text, just to make sure that there is no bad content that is happening within the platform. And actually, those models are open source, so you can use it for your own use cases. For safety, we also do bad avatar moderation, as well as bot detection, abuse report, and clickbait detection. So a lot of use cases of AI use cases being used for safety. For our players, AI drive our recommendation and search system, just to make sure and help our user to get the right content. So that means we have game recommendation, as you can see on the screen, as well as friend recommendation for social interaction. And for assets that you can use for your game or for your avatar, we also have the marketplace search driven by AI. Finally, for our creators, we introduce a set of Gen AI tools to help them improve their creative processes. And so in that example, you have a creator assistant built into Roblox that helps you create a 3x3 orb grid. That's like one set of the assistant. The other set is a script that actually helps you turn this blue orb into red and disappear when a player touches it. So similar that's what you can do as a developer using Cursor, we have the same set of tools for our creators. And more recently, we introduced our cube model. So it's a 4D object generation, and by 4D I mean it's a 3D object that you can interact and is functional. So for example, as you get a car, you can actually open the door and get into the car and drive it, and the wheel will turn. And so there's two examples on the screen. On the left side, you have a gun, a watermelon gun in the shape of a banana that actually shoots watermelon. And on the right side, you have a magic carpet built by our 4D model that you can fly. That's pretty cool. So you can see that in the future, our players and creators will be pretty much being able to create anything that they can imagine. All right, so now let's see how we actually train this foundation model and how our training infrastructure has been impacted by that. But first, let's step back and look at the AI platform as a whole to give you some context. So on the left side, in purple, you have all our data components. So starting with our data lake with structured and unstructured data, our feature store and embedding where you can, with online and offline retrieval. In the middle top, you have the blue component, which is used for training. So that's data processing. So you go from raw data to features for your training. And actually the training component itself. So when you go for features to like build those models. And then the yellow one is what we use for serving. So when you get your training and you have your model, you can push it to a model registry. And then you have our serving component that reads the model from the registry and serve it for real-time use cases, as you can see in green, and that's already described before. And finally, on the right side, you have the rest of what we use for observability, cost tracking, and our experimentation platform. So that's pretty much the AI platform as a whole. And so today we are going to focus on this red box, which is our distributed training component. So how we do multi-GPU, multi-node in a distributed training fashion. And spoiler alert, is going to use an hyperpod cluster, obviously. So let's go back to the 4D model and to the scaling factor that Michael was talking about. And so how it's going to be applied to our use case. So first was the data side. In our case, we have about 100 million 3D assets that are available. That's like roughly 6.5 petabytes of data. We don't necessarily use everything for training, but that gives you an idea of the scale. Then the model size, the requirement was between 1 billion and 70 billion parameters. So it's a very large requirement. We don't know exactly what's gonna be built. In terms of available hardware, all we know is we will need a lot of GPU memory to train those models. And so the newer the better, and H200 what we went for. In terms of training technique, the research team doesn't have any specific requirement except that it has to be performant, stable, and easy to use. And finally, probably the most important point for them is the number of jobs that they can run. And why it's more important is as we never train a foundation model, and especially a 4D foundation model, being able to run as many jobs as possible in parallel makes them more efficient and actually like refine the hypotheses that they need to create that model, and especially the model size. All right, so how does that affect our AI platform? Well, first of all, you go talk to your finance team and making sure that you have enough budget for it. That's the one. But once you get the budget, we actually sit down and look at what is going to break or what is missing from our current solution. And so we came up with 3 changes. The first one was how we actually get capacity. We already have thousands of GPU across training and inference, but those are usually like tiny GPU for inference, or they are used by other teams. And so in that case, we just needed like more capacity and more high performance GPU. And so how we get that was one change. The second change was how do we ensure resiliency? As Michael was describing, as you get more data, as the model size go up, you're most likely to fail at some point during your training. And so we have to make sure that whatever this new project is coming to the platform, we have hundreds of ML engineers working on other projects that should not be stopped because of a new project. And the last one is, okay, you get GPU, you get capacity, you get resiliency. The first one is how we make it like cost efficient and making sure that we utilize GPU resources in the best way possible. And that's where Hyperpod come into the picture and help us get there. So the first point was it's actually fairly easy to set up. It's not, don't get me wrong, it's not as easy as setting up an EC2 instances or a node group for your AKS cluster, but it's reasonable. It took us 1 month from prototyping to production. And so that includes making sure that everything that we do on the platform works the same way in an Hyperpod cluster. With InfoSec review and actually setting up the network so our AKS control plane can talk to Hyperpod nodes. And we recently created a new AKS Hyperpod cluster, and it took us less than 1 hour to do it, so I would say it's reasonable. The next point was GPU capacity. As I was saying, like we need this high-performance GPU, and so Hyperpod was one way to get there. And especially that with Hyperpod, you have like multiple options to get more capacity, either with reserve capacity, spot instances, or flexible training plan. We don't use flexible training plan today, but as we get more timely or ephemeral project, I do see that happening in the future. Continuing on how Hyperpod help us with those changes. The next one was stability. Again, as we scale up, a failure is most likely to happen, and so building those features ourselves will have take a lot of time and most likely being delayed that project. And so Hyperpod help us get there faster. And actually, as I was preparing the slide for today, I couldn't find a single node failure in the last 3 months. Even so, I can tell you that there were a lot of GPU utilization during that time, so kudos to the team. But as I mentioned, that something that is actually missing, though, is some visibility into the recurring node detection and like what failure can happen. I would have loved to show you actually a thousand of tests that AWS is running behind the scene where everything is green and everything is fine. I couldn't find this information, so we should probably take that. The last one is flexibility. And honestly, to us, that was the most important point. We already have an AI platform. We already invest a lot of time with that. We already have like tooling that we want to reuse as much as possible. And the fact that Hyperpod is able to integrate with EKS is phenomenal to us. And what I mean by that is when you create an Hyperpod cluster, your Hyperpod nodes are going to join your EKS cluster, and at that point look like just any other node in your cluster. That means that you can tend those nodes, you can do node selection, you can run any daemon set on it, and any tooling that you have, you can work the same way. And so that means that Hyperpod is actually like framework agnostics for both scheduling and training. And so in our case, that means we were able to use Unicorn just like any other AI workload that we have on the platform, and we were able to use Ray for distributed training, again, just like any other workload. So that was definitely a good selling point for us. I'll finish with what we want to build next. And that's what we call a decentralized compute. The problem still remains the same. Having access to GPU is always a bottleneck. And so Hyperpod was able to solve that in a single region, single cluster environment. But as we want to get access to more capacity, we need to extend that. And so the solution that we come up with is again, what we call a decentralized compute. And so we need a way to schedule workloads dynamically across all resources that are available to us. And it doesn't matter which region, which cluster, where the capacity is all that matters. And we need to make that in a transparent way for our user. And so how we are going to abstract the scheduling process so the user gets a unified experience and just schedule a job and submit it, and it doesn't actually care of where it's actually running. That's where we want to be. And so finally, that means that we want to extend the Hyperpod support to get like multi-region and multi-cluster for that. And so we hope to work with the SageMaker team to make that happen, and hopefully you can benefit from it as well. And that's all from me. I'll let Michael do the recap.
Thank you. Thank you very much, Denny and Tomonori. And thank you so much for sticking around. We have just 3 more slides to close out this session. And as a quick recap, we talked about the various dimensions of the critical things that are important to customers: compute availability, performance, resiliency, observability, and ease of use, and how those all apply to cost. I recall Denny talked about flexibility of choice, and on this slide, we're just going to summarize that. Right from the bottom of the stack for hardware, we have multiple options, different compute options, storage, and networking. On the software and driver layer, we have multiple pre-built images, different device drivers and toolkits. Moving further up, for multiple training libraries to ensure highly performant distributed training with PyTorch, TensorFlow, multiple capabilities for distributed training strategies, and even various MLOps third-party solutions. We integrate with MLflow or weights and biases. For tools, you can submit jobs with Ray or kubectl. For observability, like Tomonori showed, we have support for Prometheus, Grafana, or CloudWatch. You can even use SageMaker Studio or notebooks, or even use it directly from your machine to actually submit jobs. And at the top layer, whether you're using Hyperpod to orchestrate your jobs with Kubernetes on EKS or Slurm, those options are available to you. Or if you just want to use a fully managed API, you can actually use the SageMaker Training Jobs Managed API. So what this shows is we understand that for you, your use cases might be different. Your technology team might have different interests in using various frameworks. We offer that capability for you to pick and choose what works best for your use case. So we are sharing this link. It's a link to a blog where we discuss both the capabilities for training jobs and Hyperpod. It's a good resource that I usually recommend. It also has example notebooks on GitHub where you can literally just copy the code and run. So these examples are set up for you. We have hundreds of them available for you to get started. So thank you so much for joining this session, and please leave feedback on the app at the end of the day or later on. But we've really enjoyed talking to you today. We're going to also be outside if you have more questions or things you want us to talk about. But thank you very much and enjoy the rest of reInvent.